All right, let's get right into it. Today, we're taking a close look at paper 42. Think of this as a piece of focused numerical detective work. The core question here is what happens to the geometry of our system right at the edge of the mixing boundary. And the main tool for this investigation is something called the projective-diameter proxy. So, here's how we're going to break it down. First, we'll set the stage. Why was this particular probe even necessary? Then we'll look at the method, which is actually quite elegant in its simplicity. After that, we dive into the results, first for the WBA and alien kernels, and then for the Lorentzian kernel, which you'll see tells a very different story. Finally, we'll wrap up by discussing what this all means, what the study doesn't claim, and where the research goes from here. Okay, so before we can really appreciate paper 42, we have to understand its place in the larger series of papers. This isn't happening in a vacuum. It's a direct follow-up designed to answer some very specific questions that came out of the previous work. So the star of our show is this quantity right here, d of h, epsilon, the projective-diameter proxy. You should think of this as a numerical diagnostic. It's designed to give us a hard number that quantifies the geometric obstruction to mixing. In simple terms, it's a measure of how much the system's geometry is deviating from the ideal, stable conditions we see in the core. This is the setup. Paper 37 gave us this wide rigidity window where things are generally well-behaved. Then, paper 40 zoomed in and proved that within a much smaller core window, the diameter is strictly bounded by this value, d core, which is about 2.77. But, and this is the key part, paper 41 took a quick look outside that core window on a coarse grid and immediately saw the diameter proxy jump above d core. This was the first hint of a boundary obstruction. And that leads us straight to the central question of paper 42. The previous work used a pretty sparse grid. So what happens if we zoom in right at the endpoints? As we get closer and closer to the edge of that rigidity window, what does the diameter proxy do? Does it grow smoothly? Does it stay flat? Does it blow up? That's precisely what this paper sets out to investigate. So how did they tackle this? Well, the methodology here is refreshingly direct. It's not about building a whole new theoretical framework. Instead, it's about reusing existing certified tools to run a very targeted numerical experiment. The whole investigation hinges on this specific 10-point subgrid, E_by. You can see it's not evenly spaced. It's intentionally designed to cluster points near those two boundary endpoints, 0.70 on the low end and 1.10 on the high end. It's a precision probe, aimed right where the action is expected to be. And this really highlights the nature of the work. This is a pure numerical experiment. The authors literally forked the analysis script from paper 41, made just one change, swapping out the old grid for this new boundary grid, and ran it on the exact same certified Ulam infrastructure. It's all about reusing trusted tools to get a more refined view. Okay, now for the results. We'll start with the first two operators, the WBA and alien kernels. And what we find here is that for these two, the behavior on this new, refined grid is remarkably consistent and clear. The numbers really speak for themselves here. For both the WBA and alien kernels, at every single one of the 10 boundary points tested, the diameter proxy is strictly greater than the d_bound. That column on the right, the excess diameter delta, is positive across the board. There are 0 exceptions. And if we look a little closer at the behavior, we can see a couple of trends. On the upper boundary, as we move from 1.02 toward 1.10, the diameter proxy is strictly non-decreasing. It's climbing. On the lower boundary, it's what the paper calls flat positive. It's consistently above the core bound, but without a strong monotonic trend. But the main takeaway is the same for both sides, a robust, positive, excess diameter. This number is key. The minimum observed excess diameter for both kernels on this entire subgrid was just over 0.28. This means that even at its best, the system's geometry at the boundary is significantly more obstructed than it is inside the core. And at its peak, for the WBA kernel at epsilon equals 1.02, that excess jumps to over 0.67. This isn't just a marginal difference. It's a substantial, numerically observed deviation from the core behavior. All right, now let's turn our attention to the third case, the Lorentzian kernel. If the WBA and alien results were a clear, consistent story, the Lorentzian results are, well, they're a lot more complicated. And here is the big surprise. Look at this data. In stark contrast to the other two kernels, the diameter proxy for the Lorentzian is below the d-core bound at nearly all the points tested. The excess delta is negative. So numerically, on this grid, the system appears to be less obstructed than in the core, which is really not what you'd expect. So this is the major finding for the Lorentzian kernel. On this specific subgrid, there is simply no numerical support for a statement like the diameter is greater than d core plus some positive delta. Even though paper 40 proved an obstruction must exist in principle, this specific numerical diagnostic isn't seeing it here. Now, in the spirit of full transparency, the paper is very clear about an anomaly. There's a single data point where the proxy spikes to nearly 4.87, but they explicitly identify this as a known discretization artifact, a numerical quirk, not a true representation of the dynamics. So they report it, as they should, but it doesn't change the overall sub-D score trend. But here's the subtle and maybe most important part. Even though all these values are below the d__ line, they aren't static. There's a clear upward trend as you move toward the boundary at 1.10. It seems to be climbing. And that raises a really interesting question. Is it climbing towards that d__ line, and might it cross it on an even finer grid? So with all these results in hand, it's really crucial that we're precise about what this paper actually claims, and just as importantly, what it doesn't claim. And this is the bottom line. This paper is a diagnostic study. No dramatic numerical blowup was seen. No new analytic theorems were proven. The observed trends are just that, numerical observations on this specific grid, not proofs of monotonicity. And the big question about the Lorentzian kernel's behavior remains explicitly open. Everything you see here is output from an existing, certified numerical tool. So a focused study like this does what good science is supposed to do. It provides some clear answers, but it also sharpens our focus on the next set of questions that need to be asked. And the next steps are pretty clear. First, they need to run this again on even denser grids, especially near that 1.10 boundary, to see if the Lorentzian proxy ever actually crosses the d-core line. Second, they need to check how stable these numbers are by rerunning the simulations with different resolutions. And third, it might be time for a more sophisticated diagnostic tool that can give a more localized picture of what's going on. And that leaves us right here with this really tantalizing open question. For the WBA and alien kernels, the case for a boundary obstruction seems numerically solid, but the Lorentzian remains a mystery. Will a finer probe finally reveal the expected behavior, or is it telling us that there's a different, more subtle geometric constraint at play? Answering that question is what's going to drive the next phase of this exploration.